Welcome to this explainer. Today, we are diving straight into the absolute invisible backbone of modern cloud computing, distributed systems. I mean, these things are incredibly complex, beautifully engineered, and yet they completely hide in plain sight every single day. So let's pull back the curtain and look at the immense hurdles that engineers have to clear to make massive scale possible.
It really begs the question, how do giants like Google and Facebook never seem to crash? Seriously, think about it. When millions of people are searching, posting, and streaming at the exact same millisecond, there is literally no single monolithic server that could possibly handle that kind of load without just melting down. So how do these massive platforms manage to stay online relentlessly? Well, they're performing what I like to call the absolute greatest magic trick of modern computing.
All right, let's jump right into section 1, the one system illusion, making many look like one.
To actually pull off this magic trick, we build a distributed system. Now, by definition, that's a collection of independent computers that appear to be a single cohesive system designed to provide scalability, reliability, and availability. The keyword here is illusion. When you open a cloud app on your phone, you feel like you're talking to one very smart, very fast computer. But actually, scratch that. You aren't at all. You are talking to a massive network of entirely independent nodes working together so perfectly that they mimic a single cohesive machine. Moving right along to section 2, the multi-chef kitchen analogy. Okay, so think of a single computer as a restaurant with exactly one incredibly talented chef. That single chef takes the order, chops the vegetables, cooks the meat, plates the dish, and rings the bell. Now, that works great for a cozy little cafe. But what happens when 1,000 hungry customers show up at the exact same time? That single chef is completely overwhelmed. By contrast, a distributed system operates like a sprawling restaurant kitchen with dozens of specialized chefs. One is entirely focused on sauces, another's working the grill, someone else is prepping vegetables. Each chef here is an independent node. By working together simultaneously, they provide a seamless, rapid experience to the customer sitting out at the table. Which brings us to section 3, the 3 major challenges. Coordinating that many nodes is absolutely incredibly difficult. The first massive hurdle we hit is communication overhead. Back in our kitchen analogy, chefs have to constantly talk to each other to time the dishes perfectly, right? In a distributed system, computers have to constantly send packets back and forth across the network just to stay synced. If there is too much chatter, or if the network introduces latency, they end up spending way more processing power just on communication overhead than on executing the actual workloads. It's a very delicate balance to keep them communicating without grinding the entire operation to a complete halt. And honestly, that communication overhead is compounded by challenge 2, lack of a global clock. Imagine our giant kitchen again, but none of the chef's watches are perfectly synced. How do they know exactly whose order actually came in first? In distributed computing, independent machines do not share a perfect universal physical clock. They just don't. Instead, they have to rely on really complex algorithms just to approximate timing and agree on the exact sequence of events to keep the whole system synchronized. And then, what happens when things go wrong? Because, let's face it, they always go wrong. That is challenge 3, fault tolerance. What happens when the pastry chef trips and drops a cake? Does the entire restaurant just shut down? No way. Someone else steps in immediately. In a distributed system, individual nodes will inevitably fail. Hard drives crash, network partitions happen. Fault tolerance is basically the system's ability to seamlessly absorb that failure, reroute the task to a healthy node, and keep the application running without the end user ever noticing a single hiccup. So, with all this chaos, you're probably wondering, why even bother engineering around it? Well, it's because of the massive upside in scalability, flexibility, and cost-effectiveness. A distributed system can handle truly enormous amounts of data. Instead of spending a fortune to provision a billion-dollar supercomputer when you need more power, you can just dynamically spin up more commodity hardware. It provides high-performance computing in a way that is just incredibly flexible. Honestly, it's really the only feasible way to process the massive scale of data we generate today. Let's dive into section 4, scheduling, managing the madness. Okay, so scheduling is how we allocate tasks to prevent bottlenecks. It acts kind of like the head chef's ticket management style. First, we have first come, first served. It's totally fair, processing orders exactly as they arrive, but it risks head-of-line blocking if a massive, heavy task stalls the whole queue. Then there's shortest job first. This optimizes throughput by clearing quick tasks immediately, but it can actually starve longer tasks, leaving them waiting forever. Finally, round robin ensures responsiveness through time slicing. It cycles through tasks to keep everything moving, but it adds context switching overhead. Ultimately, designing a robust architecture is all about choosing the exact right trade-off for the right workload.
And finally, Section 5, powering the modern web.
Let's look at who's actually using this. Google Search relies on this exact architecture to instantly sift through billions of web pages with immense fault tolerance. Amazon Web Services, which by the way hosts a massive chunk of the entire internet, operates as a colossal distributed system, using that complex scheduling we just talked about to share resources among millions of clients. Facebook uses distributed systems to load disparate elements of your personalized feeds simultaneously without choking their database. This exact infrastructure, these massive, perfectly scheduled, fault-tolerant network kitchens, is exactly what gives us the scalable and reliable digital world we live in today.
Understanding these intense challenges is really what allows engineers to design more efficient systems every single year. But here's the thing. We are generating more data today than at any point in human history, and that trend is only accelerating. So I want to leave you with this. As our data grows endlessly, what will the distributed systems of tomorrow need to look like just to keep the illusion alive? How big can the network actually get before the nodes can no longer communicate at all? Thank you so much for joining me on this explainer. Keep learning, and I'll see you next time.